Welcome to Revolution Against Evolution. I'm your host, Doug Sharp.
Your co-host, Rich Gear, here with you, and we have a special guest that I am very honored to speak with, Dr. Raymond Damadian, and so glad to meet you and be able to talk to you face-to-face like this. And
yeah, so we're very, very pleased to be here. We're in the Phonar Corporation in New York on Long Island, and we traveled here just today to meet with Dr. Damadian and take a look at his special discoveries that he's made and learn about the MRI system that he was instrumental in inventing, developing, and making it the successval procedure that it is today.
It's an amazing thing. So, yeah, I guess I hardly know, except maybe to start at the beginning. Doug, you had a question way back in the day when you started going into this kind of stuff.
Well, there was an experiment that you did back in the day called the Caloric Catastrophe.
Yes.
And that had something to do with your discovery that led you to think that this was a possibility.
I think that the way I can begin describing this, Doug, is I was dedicated as a university faculty member to doing research, scientific research, and I enjoyed doing scientific research, and I wanted that research to be of some value, of some significance. And the one area that caught my interest in the line of research was this curiosity that the human body is a walking Con Ed plant, generating electricity as you walk around.
Oh, yeah. And
when life comes to an end, the Con Ed plant shuts down. So, what is that Con Ed plant? How do we generate voltages inside our body, allow us to move my body, allow our brains to think, allow us to move our legs, and so on and so forth? So as I began wondering about that, the first piece of the puzzle was if you looked carefully at a living cell, you saw that the living cell itself generated a voltage. So every living cell in your body generates a voltage. And that's how you become a Con Ed plant, a walking Con Ed plant. So how does that cell, like a battery, that living cell, how does it generate that voltage? And there were two scientists in Britain who got the first step. The two scientists were Hodgkin and Huxley. And they said that if you look carefully at the chemistry of that living cell, you saw a sizable amount of the atom potassium on the inside of the cell. But that atom was not a neutral atom, it carried a 1+ charge. And if you measured it, you got 140 of those potassium 1+s inside the cell and only 4 on the outside.
Oh, yeah.
So now, if you took those same numbers and put them into a battery equation, you calculate the voltage that you get in the living cell. You get a voltage across that cell of -90 millivolts. So that's where it's coming from. It was coming from the asymmetric distribution of the large amount of potassium 1+ charge inside the cell and a small amount on the outside. 140 inside, 4 on the outside.
And so you were using a methodology that I remember from my chemistry days called nuclear magnetic resonance spectroscopy, and that was a process that measured these electric voltages that you're talking about in samples.
Well, I didn't get there yet, so I have to go through another step. So.
Because I'm recalling I read your book and I was talking about they're looking, or the postulate was there was a sodium pump or something.
No, okay, that's the step I needed.
That's the way you want to go to. Okay,
that's
good. All right, we're not getting ahead of ourselves.
That's the step I needed.
Good. Okay. All right.
So you had 140 potassium inside and you had 4 outside. But on the outside of the cell, you had another atom with a 1+ charge that was sodium. And you had 140 sodium outside and 4 sodium inside. So as soon as the scientists saw that, they said, well, how does the living cell do that? How does it selectively accumulate potassium and kick sodium out? So the scientists in Britain that studied that said, it must have a sodium pump.
Okay.
There must be a protein sitting on the surface of the cell, and it pumps potassium in and it pumps sodium out. The sodium pump. Now, I was doing my research in kidney at Washington University in St. Louis, and Dr. Bricker was my professor at the time, and he said, he was explaining the pump. And I said, well, Dr. Bricker, I said, has anybody ever isolated the sodium pump? And he says, the guy who does that's going to win the Nobel Prize.
Oh boy.
So now that got my interest. So I said, all right, I got to go find that sodium pump. I got to try to write it down. And with my interest, I got interviewed by the Professor R.A.K. Solomon, who was professor of biophysics at Harvard. And he was interested in I come and do research there. So he says, Damadian, what research you want to do? And I said, well, Dr. Solomon, I'd like to isolate this sodium pump. Damadian came to the right lab. What do you mean, Dr. Solomon? He said, well, we're already working in that direction. I said, what do you mean? He said, well, my thought on the way to do this, Damadian, is to do the experiments on bacteria, the E. coli bacteria.
Oh, okay.
And then we'll try to make a mutant, Damadian, of that E. coli bacteria that can't accumulate potassium. And then we'll have two bacteria. We'll have the bacteria that can do it, and we'll have the same bacteria that's a mutant that can't do it. And now, if we go ahead and fractionate the proteins, because everybody says the pump is a protein, and we fractionate the proteins of both of them and compare the proteins, we should find the one that doesn't match up. And the one that doesn't match up, that's your pump, Damadian.
Okay.
I said, oh, well, that sounds like a good idea, Dr. Solomon. I said, but, this pump is so central to life itself and the central to generating living electricity. How do I know that I'm going to be able to even find such a pump? Because the bug that I want to be missing the pump has to be alive in order for me to isolate it. So what about that? And Dr. Solomon said, that's your problem, Damadian. Anyway, so I then started my research to make this mutant. And within about 3 months, I got the mutant. And I got a mutant that couldn't normally accumulate potassium. So now I'm ready to start fractionating the proteins and find the one that doesn't match up. So I do it for about 3-4 months at Harvard, and then I got drafted into the Air Force, and then my colonel, that was my commanding officer, liked the research that I had been talking about. He says, okay, man, you can keep doing that work while you're at the School of Aerospace Medicine, as long as you add the rocket fuel to your test tubes every so often. Because that's the one we're committed to look at, Damadian, called hydrazine. I said, oh, Colonel Bitter, I can do that. I said, okay. So go ahead, Damadian, look for your pump. So I went ahead and I fractionated the proteins. For another 2 years, I'm looking for this pump and doing electrophoresis and comparing, and I'm not finding anything. So then I got hired to be a professor at the SUNY, State University of New York, Downstate Medical Center, a big medical school. And I went and I continued my research. And I'm in the biophysics department, I'm in the internal medicine department, another 6 months. So after about 6 months of comparing this mutant to the parent strain, I'm still not finding it. So wait a minute, Damadian, one thing you ought to do, you should go to the scientific literature and see how strong is the evidence for the existence of this pump. Because if the evidence is not solid, and it's not really strong evidence, and it doesn't exist, Damadian, you'll be looking for it for the rest of your life, and they'll find it if it doesn't exist. So go check out the evidence that tells you how strong the evidence is that there is a pump that does exist. So I went to the library, intent on spending several months there to check out the validity of the evidence that there was a pump and it did exist. And I'm not there more than a few weeks, and I run into a book by a professor at the University of Pennsylvania named Gilbert Ning Ling, L-I-N-G. 500-page book entitled The Association Induction Hypothesis. in which he says flatly there is no pump.
Hmm.
That the evidence for the pump is fiction.
When was it? How was this a contemporary book at the time?
Yeah, it was a
pretty recent?
contemporary book at that time.
Okay, yeah, all right.
And it was called A Physical Theory of the Living State, and the professor was Gilbert Ling, L-I-N-G, okay? So then I said, well, now he says there's no, it provides 500 pages of proof that there's no evidence for the pump. So, and it was just a conjecture on the British professors anyway. They hadn't provided evidence for it. So then I started looking at it in more detail to see what was going on. And then the other question that came up was, if there is a pump, does the cell have enough energy to run this pump? Because the difference between the inside and the outside was large, and it was going to take a lot of energy. So then I went ahead and did experiments with Dr. Larry Minkoff at the time, and we did the experiments to measure the amount of energy that the cell could generate through metabolism to run this pump. And it didn't even come out close. The amount of energy that the cell could generate from metabolism was 14% of the calculated energy it would have to have in order to run it. And we published a paper entitled The Caloric Catastrophe.
Ah.
And so, how did this set you off into the search for that resulted in the MRI?
Well, we started publishing that, okay? And we published first the Caloric Catastrophe, Larry Minkoff and I, and then we also published some other papers where I had come to the conclusion that the evidence for the pump was not very strong, and I suggested an alternative hypothesis that was similar to what Professor Ling had proposed, and namely that this atom's got a charge. It's got a 1+ charge. So maybe it's accumulating just by sticking to the negative atoms that the cell is composed of, because the cell is loaded with negative atoms. And those are negatively charged atoms that part of the nucleic acids, they have phosphates that are negative. The proteins have carboxylate groups, they carry a negative charge. So the potassium's just sticking there. And that's how you get a big concentration. But there was a prevailing question that I had. Once you came up with that and you got rid of the pump, because the pump was doing, although the pump was fiction, the fiction was doing this that I now had to do without this fictional pump to do it. and what I had to do was account for why potassium and not sodium. Because they're both 1+ charge and they would both stick. So how come the cell was able to accumulate potassium and exclude sodium? How did it do that? And that's what the pump was providing, and we threw out the pump. And that was more difficult, all right? So in the course of doing this research, I started looking at all kinds of literature on this phenomenon. And the phenomenon was called the ion exchange phenomenon, because the cell was exchanging these atoms. And these atoms that carried a 1+ charge are referred to as ions, I-O-N-S. So we were really doing research on the potassium ion inside the cell and the sodium ion outside the cell. And that was ion exchange.
Isn't there a chromatography that's based upon that? The chromatography that works with
okay. I was
We're not
coming
there yet.
I was coming to that. All right. So then I said, well, look, if there's no pump, because we had done the evidence to show that there was not enough to run it, how does the cell make the choice? How does it carry out this necessary ion exchange? And so I said, well, wait a minute. There's a whole industry of ion exchange. Now, the chemists make these things called ion exchange resins. They're little sulfonated beads, and you take them and you pour them into a glass column.
Okay.
And you take a solution that has 10 molecules, where they're all different molecules and you would like to separate them. You take the solution with the 10 molecules, you pour it in the top of the column, it comes percolating down through the column, and you collectively successfully make test tubes, and each test tube has different materials in it, and you separate the 10 molecules. And that process is referred to by the chemists as chromatography.
Okay.
All right?
I
So
remember
this-
doing that in my chemistry.
You remember that? Okay.
So this, and the things that are doing the job for you are these little beads called ion exchange resins. And as I was doing research, I discovered that these ion exchange resins were able to make the same choice between sodium and potassium that the little cell was making.
Oh, okay.
No, wait a minute. The chemists don't have a pump to explain the bead. How do they say it's choosing potassium over sodium in their beads?
Right.
Now, the beads didn't choose it to the same magnitude of difference as the living cell, but they chose it. They have a 2-to-1 or a 3-to-1. How does a chemist explain how that happens? All right, they're looking. Sorry. Well, right off they said it was simple from their perspective. Number one, the ion was sticking to the negative charge inside the bead. But more importantly, it was tight space inside the bead.
Mhm.
And it could only accommodate so much water. And these atoms, these ions, sodium, potassium, they don't run around in life naked.
Mhm.
They have surrounding on the outside a covering of water, what we refer to as the water atmosphere. And that's the way they live. They don't live naked. They have an atmosphere of water. And what the chemists said to explain how the beads were choosing potassium over sodium, said, wait a minute. The hydrated potassium, the hydrated sodium with the water around it is bigger than the hydrated potassium.
Okay. Okay.
But specifically, you might ask, why?
Yeah.
And the answer is that the potassium atom is bigger than the sodium atom. The sodium atom is smaller. The net result is that the surface area of the sodium ion is smaller in square centimeters than the surface area of the big potassium ion. But they both have the same charge. So the charge per square centimeter is going to be greater on the 1 plus sodium than the charge per square centimeter is going to be on the 1 plus potassium.
Okay, so what does that mean?
Well, then that means that the density of charge is greater on the sodium ion than the density of that same 1 plus charge is on the potassium atom.
Okay.
All right, well, the result will be that because the density is greater on the sodium atom, it's going to attract more water molecules.
Okay.
And you won't right off know why, but the answer is that the water molecule is what we refer to as a dipole.
Mhm.
That is, it has one end of it is negative, and the other end of it is positive. So if you got a positive potassium, that water dipole will stick to it with the negative end. And that's how it puts this sphere of water on around the outside of it. Now, so when you look at it carefully then, the fully hydrated sodium ion is bigger than the fully hydrated potassium ion.
Okay. All right.
And the long and short of it is it takes up more space.
Oh, that makes more
And
sense.
if it's tight space, it's going to pick the hydrated potassium ion over the hydrated sodium ion.
So that's the reason why it does that. Okay. Now.
All right.
Okay.
But now once it's able to do that, it generates a voltage. Because you got 140 potassiums inside the cell and you only have 4 outside. And that's where your electricity comes from.
Okay.
And so you are then in the getting to the MRI story, which already we're running close to being
We're gonna
out
keep
there.
going. This is too interesting. I'm learning a lot of stuff here. You know.
But I'll get there. You got to be patient.
You gotta
All right,
go through
yeah.
this. Audience, we'll get there. It's
All right.
it's worth
No,
the story. Trust me.
I'm going there right now.
Okay, we're going there
All right.
now.
So I'm publishing this, that forget the pump, everybody. The evidence for the pump is not strong, but the way this is happening is the way Dr. Ling says, that the hydrated potassium is sticking to the negative charges on the inside of the cell, and the cell is able to choose potassium over sodium because the hydrated potassium is smaller than the hydrated sodium. So all of a sudden I get a phone call from Dr. Freeman Thorndike Cope, who was a scientist, MD, biophysicist at the Naval Air Development Center in Pennsylvania, in Doylestown, Pennsylvania. He says, Damadian, have I reading your papers? Yeah, so? Well, how'd you like to prove what you're saying, Damadian? I said, what are you talking about, Cope? He says, listen, I think I know how to prove what you're saying, Damadian. What are you talking about, Cope? He says, look, he said, if you're right, and it's because of the attachment that it's being accumulated, not because of the pump, but because that ion is attaching to negative charges on the inside of the cell, we should be able to prove that by doing NMR. We can do the NMR of the potassium atom and collect the signal from the potassium atom.
Okay.
And if you're right, Damadian, if the potassium atom is coming in by sticking to the negative charges, Damadian, it's going to change that signal. Because if it's in loose water, Damadian, and we look at that signal is going to take longer to decay than if we look at the signal of the same atom that's bound. So if you're right, Damadian, that signal should be a longer lasting signal in the potassium, in the potassium atom. When it's attached to the negative charge on the inside of the cell, that should shorten the decay time. And if it's not attached, it won't have any impact on the decay time of that signal.
Oh.
Now, maybe what I should do is just try to give an idea of this signal that I'm talking about.
Okay,
What we're talking about is this technology we call NMR, nuclear magnetic resonance. Then when we started to use it, it got renamed as MRI. But NMR equals MRI. And the reason there was the name change is when we first introduced this technology to the medical community, they wanted the nucleus, the N, to go away because it suggested radioactivity.
Right.
Right, yeah.
And when we started using it, the radiologist wanted to add the letter I to make it an imaging technology. So NMR, nuclear magnetic resonance, changed its name to MRI, magnetic resonance imaging. But NMR equals MRI. They're the same thing.
So magnetic resonance has been around for a while when you started looking at, but in real small, is that?
No, it was a laboratory procedure that they used it for.
Yeah.
No, but you're asking a good question, okay?
Yeah.
And it all goes back to the early discoveries by people, famous physicists like Isidore Rabi and others. And what they were able to show that if you took these atoms and put them in a magnetic field, and from theory they anticipated that, and then if you fed a radio signal into the atom and then shut it off, the atom would answer back with its own radio signal.
Wow. How far back is that?
So
And that was the first set
stimulate
of experiments in 1929.
1929, okay.
Does it actually stimulate the atom to do that? Is that what you're saying? Does it stimulate the atom?
Yeah, that's right. You're putting a radio signal to stimulate the atom. But I should be more specific. That radio signal is going into the nucleus of the atom. And it's the nucleus that's answering back with a radio signal.
So that's what you use to identify, based upon that signal, that's what you use to identify the chemistry that's coming back.
Exactly. Now, what Dr. Sharp is describing is that when we get this broadcast from the atom, the broadcast allows us to determine the chemistry of what that atom is doing, who it's bonded to, how many different kinds of molecules with the same atom are in it. And that ability to get a radio broadcast from the atom allows us to do a chemical analysis of the sample without ever touching it. I can do a chemical analysis of a sample just with an antenna around the outside. I don't have to go in and do a detailed chemical analysis.
This got you thinking, though, right?
Huh?
This got you thinking when you saw this.
Right. Dr. Cope calls me up, says, let's look at your theory, Damadian. So I said, Cope, so what do you want to do? He said, well, I know of a small company on the outskirts of Pittsburgh called NMR Specialties, and they have this technology, but they have a special kind of NMR machine. The present NMR machine that everybody's using, Damadian, does chemistry and does spectroscopy. So what you end up, what the chemist does is he takes this test tube, puts it on the inside of the magnet, and then he looks at the frequencies of the different atoms that are inside the test tube, and then he maps it, and that's a spectra. Mm-hmm. I'm suggesting something completely different, Damadian. We won't look at the frequencies. We will look at the signal itself and see how long that signal lasts.
Okay.
And if you're right, Damadian, and if your argument that the potassium is accumulating by sticking the negative ions, that should affect the decay time of that signal. That should affect the relaxation time of that signal, which is another name for the decay time. Mm-hmm. If you're right, Damadian. We'll measure the decay time of the signal from potassium in liquid water, and we'll measure the decay time, the same decay time of the potassium when it's inside some tissue. And if you're right, Damadian, that decay time should change markedly. If you're right, Damadian. And the way we can prove it is we just put it in this special NMR that allows us to measure the decay time of that atomic broadcast. Okay, it sounds good, Cope. What do you want to do? He says, well, right away. He says, oh, okay. And he says, I got a lab in New Kensington, Pennsylvania that will do it. We'll cooperate with us. Same place I bought my machine, but it allows us to measure the decay time. It's not good. All right, so I said, all right, let's go. Let's set up to do it, Cope. So Cope says, okay, Damadian, takes the tote, takes this test tube with the halobacter with 20 times the normal potassium, puts it inside the magnet with a coil around it, and instantly measures the potassium and measures decay time and shows that the decay time is much shorter. I said, Cope, I can't believe what you just did. He said, what are you talking about, Damadian? I said, listen, Cope, I've been measuring this potassium for several years, and I have to go through an elaborate wet chemical analysis method, and if I don't drop the test tube, and here I give it to you in a matter of 3 seconds with non-invasive electronics, you make the same measurement that it takes me days to do. I said, Cope, I can't believe what you just did. I said, Cope, do you realize that if we could ever do that on the live human body, we would be able to go from one tissue to the next and get its chemistry without ever invading anything? No, because here I am talking about a magnet that's 2 1/4 inches in diameter, and I'm dreaming about putting the human body in there, which was going to be absurd. So I says, no, Cope, Cope says to me, he says, I don't even know where you would start. I said, well, I got an idea on that one, Cope. What are you talking about? I'll do it on cancer, Cope. What's in your mind? I said, well, from everything I've read on the iron composition of cancer tissue, I know that the iron content and the iron composition of cancer tissue is abnormal.
Okay.
And if it's abnormal, the signal ought to be abnormal. And we should do it on the water signal, because I'm expecting that the potassium and sodium is going to be abnormal, so the water signal should be abnormal, and we should get an abnormal water NMR signal from cancer tissue as compared to healthy tissue.
Welcome to Revolution Against Evolution. I'm your host, Doug Sharp.
Your co-host, Rich Gear, with you as well. And we have an exciting show for you today, talking about Dr. Raymond Damadian, the inventor of the magnetic resonance MRI, basically, which is used everywhere. We had a great trip out to New York, and I don't know, Doug, you want to share a couple of your thoughts? Or I mean, there's so much to share, but I'm going to let you go in on this, because it's up your alley, really. You're the chemistry guy.
Well, we're about to go into the second half of this interview that we did with Dr. Damadian.
Right.
And in this interview, he is explaining the cancer research that he was doing back in the 1960s and 70s,
yes,
where he was trying to figure out what was really the cause of cancer and how he could detect cancer in the human body.
That's what's so exciting.
And we're just getting into the portion of this interview. If you haven't viewed the first interview before, that's on our website. Check that out. But this is the second half of it. And he's about to explain to you the breakthrough that he had in terms of the experiments that led up to the invention of the MRI.
Dr. Cope calls me up, says, let's look at your theory, Damadian. So I said, Cope, so what do you want to do? He said, well, I know of a small company on the outskirts of Pittsburgh called NMR Specialties, and they have this technology, but they have a special kind of NMR machine. The present NMR machine that everybody's using, Damadian, does chemistry and does spectroscopy. So what you end up, what the chemist does is he takes this test tube, puts it on the inside of the magnet, and then he looks at the frequencies of the different atoms that are inside the test tube, and then he maps it, and that's a spectra. Mm-hmm. I'm suggesting something completely different, Damadian. We won't look at the frequencies. We will look at the signal itself and see how long that signal lasts.
Okay.
And if you're right, Damadian, and if your argument that the potassium is accumulating by sticking the negative ions, that should affect the decay time of that signal. That should affect the relaxation time of that signal, which is another name for the decay time. Mm-hmm. If you're right, Damadian. So I said, Cole, well, what do you have in mind? He said, well, we'll measure the decay time of the signal from potassium in liquid water, and we'll measure the decay time, the same decay time of the potassium when it's inside some tissue. And if you're right, Damadian, that decay time should change markedly. If you're right, Damadian. And the way we can prove it is we just put it in this special NMR that allows us to measure the decay time of that atomic broadcast. Okay, it sounds good, Cope. What do you want to do? He says, well, right away. He says, oh, okay. And he says, I got a lab in New Kensington, Pennsylvania that will do it. We'll cooperate with. Same place I bought my machine, but it allows us to measure the decay time. Man, how good. I said, all right, let's go. Let's set up to do it, Cope. So he calls back in about a week. He says, I'm worried, Damadian. So, well, Cope, what do you mean you're worried? He said, well, I looked into the magnetic moment, how strong the magnetic moment of that potassium atom is, and it's not very strong. And I also looked into how much potassium is on the inside of the tissue to see if I can get enough signal. My problem, Damadian, is I'm afraid we're not going to be able to get enough signal. There isn't that, the potassium atom doesn't have that strong a magnetic field to begin with, and the amount on the inside of the tissue isn't all that great. And I'm afraid it's not going to work. So I said, wait a minute, Cope, I have an idea that I may be able to help. I said, what are you talking about, man? I said, I know of a bacteria from the Dead Sea that has 20 times the normal potassium. It's called Helicobacter halobium. I read about it in the books.
Say that 3 times real fast.
He says, do you think you can get it? I said, I don't know, Cope. I'll hang up and I'll start calling around, see if I can get hold of this bacteria. He says, good. Call me back and tell me if you're able to get it. So I called around a number of different places, and I was able to locate a source of this Helicobacter halobium that had 20 times the amount of potassium of an ordinary cell. So, okay, all right, man, let's go out to New Kensington to this company that has this pulsed NMR called NMR Specialties. You bring your bacteria. I know of a laboratory there where you can go and grow up the bacteria, and I'll run the machine. So I get the bacteria, and I go out, and the professor colleague of mine, Stanley Schultz, was also at the in New York. Schultz, can I use your lab to grow up my bacteria with my big vats? He said, yeah, sure. So I grow up the bacteria in these big 20-gallon vats, and then I spin it down a test tube, and then I travel over in a car to NMR Specialties, and I give the test tube to Cope. So Cope says, okay, man, he takes the tote, takes this test tube with the Helicobacter with 20 times the normal potassium, puts it inside the magnet with a coil around it, and instantly measures the potassium and measures decay time and shows that the decay time is much shorter. I said, Cope, I can't believe what you just did. He said, what are you talking about, man? I said, listen, Cope, I've been measuring this potassium for several years, and I have to go through an elaborate wet chemical analysis method, and if I don't drop the test tube, And here I give it to you in a matter of 3 seconds with non-invasive electronics. You make the same measurement that it takes me days to do. I said, Cope, I can't believe what you just did. I said, Cope, do you realize that if we could ever do that on the live human body, we would be able to go from one tissue to the next and get its chemistry without ever invading anything? No, because here I am talking about a magnet that's 2 1/4 inches in diameter, and I'm dreaming about putting the human body in there, which was going to be absurd. So I says, no, Cope, Cope says to me, he says, I don't even know where you would start. I said, well, I got an idea on that one, Cope. What are you talking about? I'll do it on cancer, Cope. What's in your mind? I said, well, from everything I've read on the iron composition of cancer tissue, I know that the iron content and the iron composition of cancer tissue is abnormal. And if it's abnormal, the signal ought to be abnormal. We should do it on the water signal, because I'm expecting that the potassium and sodium is going to be abnormal, so the water signal should be abnormal, and we should get an abnormal water NMR signal from cancer tissue as compared to healthy tissue. So I was wanting Cope to collaborate with me. Well, he thought it was off the wall. He really didn't want to go forward and do it. So I went to the president of the company, Paul Yaiko, and I said, listen, I have this idea. Maybe, if it's kind of a wild idea, but I said, if at least we can show the signal is different between cancer tissue and normal tissue, we can talk about building a scanner for the human body. So Yaiko says, fine, come back when you're ready.
What time period are we talking about right now? What year was this?
Well, the original proposal I had was 1969.
1969, okay.
So it says, fine, come on back, go home, get your animals, whatever you want to do, and bring them back, and I'll let you use the scanner under one condition. You don't use any of my personnel to run the scanner. You got to do it on your own while you're here. And Cope had done all the measurements, so I didn't even know where to start, which buttons to press, okay? So I get back there, and he hands me the spectrometer and a test tube and a magnet. And he hands me the manual. This is the operator's manual, Damadian. So I said, all right. So I start measuring on liquid samples and test tubes and so on and so forth. And I do several weeks worth of work and finally get to the point where I can trust the numbers I'm getting. And I'm getting reliable numbers. So I said, okay, the big moment. And I had some rats with me that had cancers in them. And so I cut the tumors out, put them in a test tube, put them in a magnet, and did the same thing with the healthy tissue. And I measured the decay time of this signal. And the decay time of the cancer tissue was dramatically different than the decay time of the healthy tissue. It was much longer. So I said, holy smokes, it's actually working.
This actually works.
The signal from cancer tissue is dramatically different. This is something that we could potentially non-invasively scan.
And were you still doing this on the little?
Doing on a little test tube.
Little test tube, okay.
I cut the tumors out, put it in a test tube, put a test tube in.
Okay. Tiny little thing. Okay. All right.
So, because it was such a dramatic result, we published it in this world famous journal, Science, and it appeared in print in 1971. And the other thing that was stimulating our interest in is at the exact same time, President Nixon had announced that he's going to commission a war on cancer, and he's going to provide $1 billion a year in research funds to people to overcome the disease of cancer, which of course meant that I was going to have an ample supply of research funds to do this research. I get a phone call from the head of the cancer diagnosis program, Dr. Ken Olson, who had been assigned this responsibility as a professor himself of overseeing the Nixon Cancer Detection Program. And Dr. Olson called us and says, Damadian, I read your paper in Science. He says, it's very interesting. He said, we want to follow up on your research. We want to use the research program that has been put forward by President Nixon to follow up and see how far. First we want to do is validate all the numbers that you got, and then if everything is working, we'll try to proceed to make the scanner that you have in mind for scanning the human body. I said, well, that sounds great. He said, we're going to put out a contract. The contract will provide $100,000 a year, and we'll let everybody compete. And if you win Damadian, you'll get $100,000 for 2 years, $100,000 a year for 2 years. And we're going to have the contract available to 3 research scientists, so everybody can compete, but we'll only select 3. So he says, well, go ahead, Damadian, and get started. So I get started. The contract, we compete, and we get the contract, and a group at Baylor University in Texas gets a contract, and a group at Johns Hopkins gets a contract. And then Dr. Olson calls for a convention of all the people who have been working under the Nixon program for cancer diagnosis. And ours was only one segment of this, but he holds a big conference at the National Cancer Institute in Bethesda, Maryland. There's hundreds of scientists come from all over the place. And our section on the NMR, the MRI, is only one small section of this whole collection. So as different scientists start giving their report, it finally comes to the cancer detection, NMR cancer detection, that our 3 scientists are part of. Okay? Says, all right, Dr. Damadian, I want you to go first. You tell what your results have been. So we get up, and we had now made the measurements on cancer tissue in live mice. And we made some images and pictures, and we were able to see the tumor in the live mouse. Then the next scientist, Dr. Hazelwood, from Baylor University, gets up and he says, all right, I did the measurements for the past year, and I measured the T1 and the T2 of cancer tissue, like Damadian, and I got the same abnormal T1 and T2 that Damadian got from his signal. Now, I should tell you what T1 and T2 was just briefly.
That would be
okay?
good, yeah.
What?
That would be good.
Okay. And it's very simple. As I said, we're collecting from the body a radio signal from the atom. And what we do is we stimulate that atom to give back its own radio signal. So we pump in a radio signal, and then we wait for the signal to come back and pick up on the antenna. And the signal that comes back doesn't last forever. It starts off big, as you would anticipate, and it slowly decays. And what we measure is the decay time. And there are 2 decay times that we measure, and they have names. The T1 decay time and the T2 decay time. The T1 is called the spin lattice relaxation time, and the T2 is called a spin-spin decay time, but there are 2 decay times. And we measure them, and they're different, okay? So I'm able to give my report and say that we've been able to measure this in the live mouse, and we got the same abnormal T1 and T2 in the decay time from the live mouse that we got in our test tube samples. And Dr. Hazelwood gets up and says he had measured the T1 and T2, and he got the same delayed T1s and T2s, the longer decay times that Damadian got. Then the 3rd professor from Johns Hopkins University, Dr. Hollis, gets up and he gives his presentation, and he said, okay, I measured the same decay time of T1 and T2 that Damadian measured in cancer tissue, and I got the same delayed decay time that Damadian got in cancer tissue.
So this is 3.
Huh?
This is 3 different. You and 2 other people have gotten the same results.
But I'm not done yet.
Okay. I'm trying to follow you clearly. You know.
All right. So the 3rd doctor who has done the research, Dr. Hollis, said, I measured the T1 and T2 of cancer tissue and compared it to the decay time of normal tissue, and I got the same abnormal decay time that Damadian did for cancer tissue. But
okay,
I measured the same signal from diseased tissue that was not cancerous, and I got the same decay time that I got for the cancer tissue. Therefore, ladies and gentlemen, any further discussion about scanning the human body by NMR is visionary nonsense.
Oh boy.
Because you can't distinguish cancer tissue from
Okay,
other disease tissue.
but they're cancer's disease tissue as well as others. I mean, so is the difference between both the disease, which is not cancerous, and cancer cells, is that different from healthy cells?
Well, you're asking the key question.
That's
Okay.
okay. All right. So okay.
No, but because that became a central issue, and we ended up after all this was done, we ended up in a big patent fight with General Electric, okay?
Oh.
And General Electric made the same argument. General Electric said, wait a minute, you got an abnormal signal for a cancer tissue, a delayed decay of cancer tissue, but you get the same abnormal signal from other diseased tissue. And the response is, yeah, but you got delayed signal, an abnormal decay in two diseased tissues that were different, both of them were different from the normal.
Yeah.
And our attorney said, now wait a minute, GE has argued that you got an elevated signal from cancer tissue and the same elevated signal from other diseased tissue. Ladies and gentlemen of the jury, you're going to punish the guy because his original discovery detects more disease than he originally imagined?
That's what I was getting at. Yeah. Okay, yeah,
Oh, yes,
yeah.
there you go.
So gratefully, we won.
You won.
The jury found in our favor, and the judges upheld it. And then the other amusing aspect of this is that after we won, the award was $129 million.
Yeah. Yeah.
And the head of the jury came up to me on the decision, and it said, she said to me, if it hadn't been for the men on the jury, your award would have been $400 million.
Now,
The ladies wanted to give you $400 million.
at this point in time, had you come up with a full-size body scanning thing yet? Was this before or after?
Yeah, no, let's see now, when did this, yeah.
The lawsuit was about, weren't they
No,
ripping you up?
no. We had built Indomitable,
Yeah.
and we had by this time we had a full size body. We had Indomitable. We had
Let's
done-
talk
we had
about
done-
Indomitable a
We had
little
done the
bit.
first camp, but yeah, just
Yeah, okay,
Just let me just finish this point. So
Okay.
after we get that decision, I get a phone call from the CEO of General Electric.
Jack Welch.
I get a phone call from Jack Welch.
Yeah. Big dude.
And Jack says, Dr. Damadian, this is a phone call I should have made a long time ago. He said, but I want to talk to you about reaching a settlement on this patent dispute between your company, Fonar, and GE. So he says, I'd like to come and meet with you. He says, I'll come to Fonar Incorporated with me. I said, no, wait a minute. Dr. Welch, that makes me a little nervous. I said, I don't want to meet with you without my lawyers present because I don't want to end up saying something that's wrong that's going to end up
Right.
fouling this all up.
Exactly.
So he says, okay. Where do you want to come? I said, well, if you don't mind, when I have my lawyers, I said, we can come to your main offices in Manhattan. He said, oh, okay, fine, man, come to the office in Manhattan. So we go to the offices. I go there with my two lawyers, and with Jack Welch and me. And we had sued them on two patents. We had sued them on my original patent, which was the discovery of the T1 and T2, and we had sued them on another discovery that we made, where we were allowed to, we came up with a technology that allowed us to make the cuts, the slices of the MRI at different angles. An oblique would make slices. So we had, and they were using both of them. So we sued them for patent infringement on both those patents of our company. So Jack Welch says, okay, Damadian, he says, I'm ready to go ahead with a settlement, and what I'm going to propose is that I'm ready to write a check right now for $80 million. The award had been for $129 million. He said, but we're going to take your original patent, the first one, the 832 patent, we're going to set it aside. We'll pay you on the second patent. I said, well, but that's tough on me, Mr. Welch. I said, because that's a hard one on my soul. That's my heart and soul. And you're just setting it aside as though it's an insignificant event.
Because that T1, T2, that's the primary discovery.
Oh, the T1s and T2s,
Yeah,
that's
that's
right.
the primary
And you're
thing.
just setting it aside as though it's irrelevant. I said, that's a hard. Well, as I'm doing that, the faces of my two attorneys are turning very grim because they had taken the case on full gratuity. Namely, if we didn't win, they didn't get anything. If they did win, they got $40 million. They got 40%.
32 million.
So that would be $50 million. 40% of $129 million is almost $50 million. So the legal fees that they were going to get was $50 million, and I just turned it down. I said I can't.
when I was reading your book, maybe I got this wrong, but I thought in the book, I remember reading that he was going to write you a check for $80 million.
That's right.
Instead of the full $129 million.
Oh, no, there was no. It
Yeah,
was
the
80
word-
million.
Yeah,
It was 80 million instead of 129.
that's what I'm saying, yeah, and they would have got 40% of that.
They would have gotten 40% of the 80 million. They would,
Yeah.
I said the wrong thing.
Yeah, that's what I was
They
getting
would
at,
have
okay.
gotten 32 million.
Yeah, that's
Yeah.
what I'm saying, okay.
Yeah.
Yeah.
They would have gotten 32 million.
It was still a lot of money.
And I-
They were going to lose out on
And
potentially.
I was turning down that $32 million.
But it's interesting because when we read the book, what was the reasoning that you had for turning that down? I mean, $80 million is a lot of money to walk away from, you know? I know that there's a thing there, but it's like there was something in you as a person that would not settle for that for a good reason, and I love it when the way you put it in your book. And there's something about truth, about integrity. Just there's some things about it you were talking about that.
No, I wouldn't say it was integrity so much as what they were doing is disqualifying my discovery.
Yeah.
In other words,
Right.
they were saying my discovery is of no consequence.
And that wasn't true. That wasn't
And
real.
no,
Yeah.
I mean, the whole industry was running off my discovery, and they were disqualifying the discovery,
Right.
and that was painful for me, because I'd given my life to that discovery, and they're just shoving it aside. And they would be anybody would be in a position thereafter to say that the discovery was of no consequence.
Right.
So that was very painful for me. But it was even more painful for my attorneys.
So then you actually did go into the court, and you
Yeah.
still won.
No. So what then
Yeah.
happened was, we're going to take it to the Supreme Court, because that's what he said. If you don't settle for
Yeah.
this, G's going to take it to the Supreme Court. So he sent it to the Supreme Court. At that point in time, just by coincidence and timing, I had been invited to make a presentation of this new MRI, NMR technology to the armed forces. Specifically, I was invited to the United States Air Force, a big convention, the United States Air Force. They wanted me to present to all their Air Force scientists this discovery of T1 and T2. So I'm down there in their headquarters, and there's probably a dozen Air Force generals that they asked me to come and speak to, and I'm down there with our executive, Lou Benanti, who's our executive vice president at FONA. And while I'm talking to the generals, suddenly somebody comes in from the outside, and Lou Benanti comes in and says, "Dr. Main, you got a phone call from your lawyers on the General Electric case, and they want to talk to you." So I said to the generals, I said, "If you don't mind," I said, "we have this case that's been pending against General Electric. It has gone up to the Supreme Court, and my lawyers need to talk to me." So I go over to pick up the phone, and Lou Benanti's standing there with me. And my lawyer says to me, "Well, Damadian, you don't know this yet." He said, "We just got the decision from the U.S. Supreme Court from Judge Rehnquist to GE. The decision is GE, pay FONA, pay him now."
Yeah.
Oh, no.
Yeah.
So the two of us start jumping and with our arms around each other, jumping and screaming in ecstasy.
But who else-
and
who
and the
else-
judges come running out of the room to see what in the world is going on.
Who else was with you jumping?
Lou Benanti.
Okay, yeah.
He is our executive vice president.
Now, by this time, you've already had the Indomitable up.
Oh, that's right.
So I'd like to go backward just a little bit and talk about the process of when you come up with what you called Indomitable. That's why I say this thing with the case, it seems more like almost like your indomitable spirit, or with that thing that the Lord's put in you, just to carry through. But
Which is the very first MRI.
the
that
very
was
first MRI, and there's a lot of stuff that was going on. This is a very interesting and fascinating story.
And at one point in time, that the machine was at the Smithsonian.
Is it still there, or is it not there now? Is it
I don't think it's
No,
there.
I think it's not there now. It was big and taking up a lot of space, and they have it all in boxes right now. The latest I've heard on that.
Yeah, they've got a lot more.
But it was there for a while.
Better retrieve
so
it
the
and
question is,
put it back on display here, right?
yeah, no, that's the right thing to do.
So you took this idea, it seems to me, that this little thing inside this little 2 1/4 inch, and then you got this idea you could maybe do a full body thing, and that's where. And by the way, that's where all this court case came from, because there were other people starting to once you had figured it all out. But what were some of the things that happened? I mean, it's a very fascinating story because the perseverance to go through this, the keep going on, it's a fun story. And you had a lot of associates that were with you along the way. When we tell the story, it's kind of some humorous things there a little bit. When you talked about the time you trying to get it. Well, the first thing is that and I'm jumping around a little bit. You're needed to get a wire to make it or something. And tell us about that a little bit.
Well, the long and short of it, and the reason there was so much ridicule, is that we're talking about taking an analyzer of a 2 1/4 inch test tube and replacing the test tube with the human body.
Yes.
Mm-hmm.
And hey, yeah, we're going to put the human body in that 2 1/4 inch magnet. Well, it's obviously not going to put it in a 2 1/4 inch magnet. Right away, you realize you're going to have to build a much bigger magnet. And then the antenna is going to have to get much bigger, because instead of the antenna going around a 10 millimeter test tube, the antenna is going to have to go around a 20 inch body. Well, everybody thought the whole thing was ridiculous, because when the key to this whole technology was the signal that we talked about initially, the radio signal coming from the atoms. And the big fear that we all had was when we're going ahead and trying to detect a small tumor in the center of the body with an antenna that's 10 inches away, when the normal antenna is 10 millimeters away, that everybody said it was ridiculous, you'd never get enough signal. But anyway, we had now come to the point that it was unequivocal that the signals from cancer tissue were different from normal, and so now if we were going to go forward, we'd take the next step and build a magnet big enough to put a human being in, which was a real tough go, because everybody thought it was absurd.
It's 1977 at Downstate Medical Center in Brooklyn, New York, today known as the State University of New York Health Sciences Center in Brooklyn. Dr. Raymond V. Damadian, then a faculty member, and his 2 graduate assistants, Larry Minkoff and Michael Goldsmith, has spent a year of nearly round-the-clock work in a stark university laboratory, building a machine that would, they hoped, scan the human body using the principle of nuclear magnetic resonance. Not only something never attempted before, but something never even thought of before. They called the machine Indomitable. For Dr. Damadian, it was an all-out attempt to realize a dream, born out of his work done several years before on the NMR relaxations of normal and malignant tissues. But would Indomitable ever work? This tremendous effort, punctuated with frustrations, disappointments, and financial difficulties, would it ever pay off? It did. At 4:45 a.m. on the morning of July 3rd, 1977, Indomitable produced the world's first MR image, a cross-sectional view of Larry Minkoff's chest. The scan took nearly 5 hours to complete. The MRI industry was born.